Okay, so the first thing we're going to do in this three-phase unbalanced delta load is we're going to find currents, and we're going to do that by evaluating each phase as you pointed out. So if we look at I of AB, it's going to be equal to voltage AB divided by impedance AB, which in this case is resistance AB. Now, I just want a little bit thinner line, so just hold on a second, you guys. I like the thinner line personally. All right, so if we apply some numbers, that's better. 240 volts, and we divide that by 10 ohms. Pretty basic math tells us we're going to get 24 amps. Now, we want to put an angle there. Given that it's a resistor, what would our angle be here? 0, good. 0 simply indicating that the current is in phase with the voltage. Yeah. Let's look at current. What's our second current going to be? What's our second phase? What's the subscript? Heard somebody whisper it. BC. BC, thanks Neil. BC is correct. So we're going to look at voltage BC. We're going to divide that by impedance, or in this case, resistance BC. And we end up with 240 volts. We're going to divide that by 20 ohms, which gives us 12 amps. And once again, because it's a resistor, we will be at 0 degrees. Again, just indicating that we are in phase with the current and the voltage. That brings us to our last phase current. I of CA is going to be equal to voltage CA divided by impedance or resistance CA, 240 volts divided by 40 ohms, and that gives us 6 amps, again at 0 degrees, just indicating that we are in phase. So math here isn't really too tough. Where it gets a little tricky is how vigilant you are and how neat you are once we get to the Cartesian plane, because we all know that these particular angles that we just looked at are not all going to be at 0 degrees. They're going to be in relationship to the voltage that caused them. So let's go back to, I guess this is going to be at the top. Let's go up here. Where's my Cartesian? Oh, it is on the next page. Yeah, right here. Okay, so what I've done for you guys here and on your handout, you will notice is I've already put in the solid black lines are indicating our three main phase voltages. Now, what do we know about a delta as far as phase voltage and line voltage are concerned? They're the same, right? So we can make the statement then that voltage line equals voltage phase in a delta. Now, the currents, of course, in an unbalanced delta, can we use the statement that our line current is equal to √3 times the phase in an unbalanced delta? No. Can we in a balanced delta? Yes. Seeing as how we do not have a balanced delta here, we have to look at each individual phase. Now, you guys have already done the math for each phase here. So step one, and the easiest thing to do, is to go and identify our phase or line voltages, and then look at the reverse or the 180 degree out of phase displacement voltage from that. So over here, this is going to be voltage AB. I'm not going to put values in here, you guys. You guys noticed yesterday it's really tough for me to get all of the information on the smart board here as far as providing a value and angles and all that. So I'm going to count on you guys to kind of help me out with that. So there's voltage AB. Where would we plot voltage BC? Here or here? There. Right here. This is voltage BC. Remember, direction of rotation, in order for us to keep what's called positive phase rotation, we look at our phasors as going counterclockwise on the Cartesian plane. That, of course, means that up here we have voltage CA. All right. Now, if that's voltage AB, what would we call this guy 180 degrees out of phase? VA. Good. Voltage VA. And then, of course, voltage BC, this would be voltage CB, and this would be voltage AC. Now, why do you think that's going to be important here?
Figuring out your line.
For sure. When we go to take a look here, and I'm going to just backtrack to this screen here and take a look. So when we want to calculate this current right here, that's going to be the vector sum of what two phase currents?
AB and AC.
AB and AC. So AB is easy. We all know where voltage AB is at in the Cartesian plane, right? On the Cartesian plane, voltage AB is right here. Where's voltage AC? If we didn't put that in, you're going to have to figure that out. Well, voltage AC, of course, is 180 degrees out of phase with voltage CA. Okay? So when we go to plot our currents, this is going to become very important. So when we go to plot our currents, I'm just going to start by doing some calculations here. Actually, no, we're going to go to, and we're going to actually plot them first. Just about stepped out of line here. Okay, let's start with current AB. Current AB is 24 amps. So we're going to use a line. And we want to do this guy, and we want to make it red. And it's 24 amps, and it's in phase with voltage AB. So this is an easy one. Right here, we have, and I'm going to go way out here. Okay, that is current, whoops. Back to pen. So here is current AB, and of course we know that's 24 amps and that's 0 degrees, right? And again, I'm going to have you guys write that in. I just am not going to have room up here to write all that information. Now, what I like to do, but I'll leave it up to you guys, while we're at it, does it make sense for us, because we're going to need to know where it's at some point, why don't we draw in the phasor voltage or current VA while we're at it? We're going to need to know where that's at some point, right? So let's do that. So same thing going the other way here. I'll just tell it to do that. Come on now. So we're going to go here, and that's current AB. Or current BA rather. So it also is 24 amps, but of course we know that that current now is going to be at 180 degrees, not at 0. Good. Let me see if I can move this up just a tad. Good. All right, let's go and plot current BC. Again, current BC is pretty simple because it's in phase with voltage BC, and we know that voltage BC is down here. So we're going to put it in. Now, it's not quite as long as current BA. As a matter of fact, it's only half as long. So if we count kind of our little red circles, what do we have here? 1, 2, 3, 4, 5. So we need to go about 2.5. So let's do that. We're going to go 2.5, 1, 2.5. We're going to do that guy, and we're going to do this guy at the same time. Why not? Okay. And so that is current BC, and this is current CB. And we're going to do the same thing with current CA. And it's only half as long again, and the current CA is in phase with voltage CA. So if we went 2.5, we're going to go about 1.5 here and do something like this. Something like that. So here we have current CA and current AC. Now you guys all know what those values are based on the math that you've already done. Okay? All right, so now that we know where all these currents are physically located at on the Cartesian plane, Now we can actually add up our line currents. The reason we're doing this is when you guys in industry go to put your amp clamp right here, you want to know what's it drawing. If we have an unbalanced load, we need to know what does this amp meter right here read. And likewise on both phase B and phase C. And that's the practical side of what we all do. Right? The theory leading up to why that number appears on your multimeter, that's what we're covering now, but the reality is, what is it going to say? So, this is where math comes in. I'm going to extend the page here. Now, it's up to you guys, but I like to kind of complete some due diligence here and write this out. So I like to do this. I of A is equal to I of AB, and I think Devin already pointed this out, plus I of AC. And we know that I of B, same idea, but let's start with some numbers here. So I of AB, is 24 amps at angle 0 degrees. That's pretty simple. That's where it was located on the Cartesian plane. Now, where is current AC and how much is it? Where is it located? How much is it?
24 amps at 330.
24 amps? Nope. It's 6 amps. Yeah, at 300. So let's take a look at that. So I'm going to just go up here. Let's find current AC. Where's current AC? Here it is right here. So it's 6 amps or 6 units long, and it's at 330 degrees. So when you guys are doing and plotting the voltages, I had already kind of given you that. It's always a good idea to go and stick the angle that that voltage is at, because it's going to help you later on when you have to plot your currents, and particularly when you have to add them up, right? So, given that, if we add,
It's 300.
it's 3, yeah, it is 300. As you guys are questioning, well, wait a second, that should be 300. Good call, good catch. What an awesome crew. Wow, 300. Thank you, degrees. Yeah, 330 is halfway in between, isn't it? Yeah, good. So yeah, and that's what I mean. Like, you can see how easy it is to make a mistake. You get your voltages wrong, your currents are wrong, then your end result is wrong. So it's kind of a cascading question in sorts. So if we add those up on mode 3, what do you get?
27.495.
Hold that thought. My return should be. There we go. What in the hell? There we go. Thank you. All right, you said 27 point what? 495. Thank you. Now, big question. Where'd that end up? What angle?
Negative 10.89.
Negative 10.89. Now, could we represent the negative 10.89 as a positive value? Yeah, you just take your 360 degrees, subtract 10.89, right? Good. And we're going to go and we're going to plot this on the Cartesian plane when we're done calculating our 3 line currents. We'll go show you where it's at. So that brings us to our next one, I of B. That's equal to I of BA, or sorry, I of BC rather. Doesn't matter what order you put them in, I suppose. Plus I of BA. My board's working pretty good today. Okay, I of BC. We should have 12 amps at an angle of what?
240.
240, good. Plus 24 amps at an angle of 180. We add those two using phasor addition. And if you've done it right, if I've done it right, correct me if I'm wrong here, you should come out to about 31.74 amps at an angle of, I have negative 160.89. Anybody else getting that?
Yeah.
Yeah? Okay. Again, we could represent that angle as a positive. We just have to take away 360 from that, and that would give us our positive value. All right, let's look at I of C. So our amp clamp, when we put it on I of C, what would we expect to find? Well, it's going to be the vector sum of I of CA plus I of CB. And the values associated with that should be 6 amps at an angle of 120 degrees plus 12 amps at 60 degrees. And if I've done it correctly, I got 15.87 at an angle of 79.1 degrees. Is that right? Okay, good. We're on the same page. All right, now what we're going to do is we're going to go see where these currents actually end up on your Cartesian plane. We're going to go back here and we're going to start with current A. We said it ended up to be 27 units long, approximately at minus 10. Wonder if I have a nice picture. I think I do here. Yeah, to help me out. So I of A, let's use a different color this time so we can demonstrate where the resultant was. Let's use lime green. That looks interesting. And so we said negative 10, so that's negative 15, so somewhere there we had this guy. And then go here. So that is I of A. Okay. I of B we said was 31.74 amps at negative 160. So it's somewhere over here, and it's quite lengthy also. And that is I of B. And lastly, I of C, we said was 15.87 amps. And it ended up at 79.1 degrees. So somewhere, if that's 90, something like that. And that's I of C. Everybody good with that? Is all the problems we're going over, you guys, if you haven't already done some of them, you're going to get problems just like this, probably even harder. So hopefully this will give you a foundation for that. All right, let's talk power. So we're going to insert, let's just do a blank page. I like blank pages. All right. In order to calculate power, I want to touch again what I kind of touched on this at the beginning of the lesson. Can we use our root 3 formulas? Can I go E line? Well, let's write it out. Can I do this? And I don't want it to be lime green, so let's go black. Can 3-phase formulas be used? And I'm going to write them out just so that you remember them. So power total is equal to E line times I line times what? Root 3? Good, times power factor. Q total is equal to E line times I line times root 3 times what? Sine theta. And then, of course, apparent power, which is S total, is simply equal to E line times I line times root 3. Now, the question is, can we use those in an unbalanced system? And the answer is no. Only can be used on a balanced system. Okay, that means we have to add our powers up individually per phase. So let's start with power AB. What's our formula going to be here for finding our power for each phase? We could use I squared R, but what other information do we have that's probably a little bit more pertinent?
VAB times IAB.
So VAB times IAB. So basically, so your I squared R, that'll work, but we would have to go and find, I guess we do have R, don't we? So in fairness to answer your question, that's probably just as easy as this one. So yeah, that one would work pretty good too. I just did it this way and I'm lazy. I don't want to have to go calculate it the other way. Now, what about power factor? Don't forget that. Is that important here on this particular question? No, why not? We're in phase. What is the cosine of 0 degrees? 1. So we're going to be timesing everything by 1. Okay, and I actually did that just for demonstration purposes, but let's throw in some numbers there. 240 volts times 24 amps times 1. And I came out to 5.76 kW. Bless you. Now you'll notice I'm representing this in kilowatts, right? Because we are over 1,000 watts. Let's look at power BC. Same thing, we're going to take 240 volts, multiply it in this case by 12 amps, and we don't really have to multiply it by 1 because we already know that 1 by itself is, it's not necessary to put it in there. And I got 2.88 kilowatts. And on power CA, 240 volts times 6 amps, which is 1.44 kilowatts. Now, power total. It's real simple. We add them up. So that's going to be power from AB plus power BC plus power CA. And if you add all three of those together, you should come out to 10.08 kilowatts. That's good. Any questions on power? Pretty straightforward. All right, that does our delta. Now let's move on to one that gets almost every single student, and that's problem number 6. This one right here. I'm just going to stop the recording for just a second. Stand by, guys. I'm kind of doing a recording at the same time, so I just want to